Okay, I will share my screen. Okay, everybody can see my screen. You can hear my voice.
Boleh, Doktor.
Okay, thank you for the response. Okay, so today we will learn about chapter 2, which is about the noise. Okay, so this noise will come out in the test and also in the final exam. Okay, so this is yeah, most of chapter 2 is about calculation. Okay, calculation topic. So you will need a calculator to do the calculations. Okay, so hopefully if we have time later, I will show you example of the previous semester's test about noise, so that we can try to answer the question. Okay, so this topic, this chapter covers up to 7 subtopics. Okay, type of noise, noise spectral density, signal to noise ratio, SNR. Okay, so this is the SNR. And then noise factor and noise figure. So noise factor is, the parameter is F, noise figure is NF. Okay, noise figure. And then Freeze formula to calculate the noise factor, and then you can find the noise figure. Okay, equivalent noise temperature, this is a TE parameter, and then this is noise measurement, which is about noise voltage. This is about noise voltage. Okay, so let's look at type of noise. Okay, types of noise. So these are the types of noise. Okay, so noise has a big family tree like this. So maybe there's a student want to attend this class, so maybe I need to accept. Okay. Okay, so noise has a big family tree like this. So type of noise, it can be divided into 2 categories. The first one is correlated noise, and then uncorrelated noise. Okay, within the correlated noise, there is a non-linear distortion noise, which consists of harmonic distortion and also intermodulation distortion. Okay, and then uncorrelated noise, we can further divide it into external noise and also the internal noise. So when you see external, means that the noise produced from outside of the transmitter and receiver. And internal noise is the noise that generated within the system, which is within the transmitter or receiver. Okay, so in the external noise, external, outside from the system, so there are atmospheric noise, extraterrestrial noise, man-made noise, impulse noise, and also the interference. So within the extraterrestrial noise, so extraterrestrial noise are the noise that generated from outside of this earth, which consists of solar noise and also the cosmic noise. Okay, and then if we look into the internal noise, which is the noise generated within the transmitter and receiver, it consists of short noise, transit time noise, and thermal noise. Okay, so these are some of the type of noise. Okay, and most of the content in this chapter is about thermal noise. So you will learn a lot about thermal noise. So thermal noise is a noise that is correlated with the temperature. The higher the temperature, the higher would be the thermal noise. Okay, so we will see about this later. Okay, because most of the topic in chapter 2 and also the calculations topic are related to the thermal noise. Okay, and for your information, in the previous semesters, there's a one time, I think more than one time, that we provide this picture, okay, these boxes, these three, and this has been asked in the previous semester's test long time ago, okay, before the COVID pandemic. Okay, so what we did was we give this family tree and we leave some boxes empty. So students need to fill in the boxes with the related type of noise. Okay, pernah keluar soalan yang ini exactly the same like this. Okay, so next, the type of noise, as we seen from the previous type of noise, we can see that the noise can be divided into two: correlated noise and uncorrelated noise. Okay, so correlated noise, okay, implies the relationship between the signal and the noise exists only when the signal is present. Okay, so that means, for example, here, if I draw like this, so correlated noise exists when there is input signal. Okay, so if there is no input signal, then there is no correlated noise. Okay, hanya jika ada input signal, then there gonna be correlated noise within the transmitter system, okay, and also within the receiver. Okay, because this input will mix up with the carrier, and there's gonna be no additional noise within the system. Okay, uncorrelated noise present at all time, whether there is a signal or not. Under this category, there are two broad categories, which are internal and external noise. So that means uncorrelated noise exists at all time, regardless whether there is an input signal or not. Okay, tak kira sama ada input signal ataupun tidak, maka uncorrelated noise still exists. Okay, so it can be divided into internal noise, which is generated within the transmitter and receiver, and also the external noise, which is generated from outside of the transmitter and receiver, which is within the medium, okay, in the medium. So let's look in the uncorrelated noise. Okay, uncorrelated noise can be divided into external noise and also the internal noise. So external noise is a noise generated from outside of the device of circuit. There are three primary sources, which are the atmospheric noise, extraterrestrial noise, and also the man-made noise. Okay, so atmospheric noise is a naturally occurring electrical disturbance originate within the Earth's atmosphere. Okay, it is called as the static electricity. Okay, most static electricity is naturally occurring electrical conditions such as lightning. In the form of it is in the form of impulse, spread energy through wide range of frequencies. It is insignificant for frequency above 30 megahertz. So this atmospheric noise is insignificant if we have signal more than 30 megahertz. Extraterrestrial noise consists of electrical signal that originate from outside of the Earth, okay, which is in the deep space noise. Okay, which is in the deep space, outside from the Earth, which is in the space. Okay, so it is also known as the deep space noise. Okay, so extraterrestrial noise divided into two categories, which are solar noise and also the cosmic noise. So solar noise is generated directly from the sun heat. So there are two parts of solar noise, which is quiet condition and also the sporadic disturbance. So solar noise is the noise that generated due to the sun activity. Okay, and then the cosmic noise is the continuously distributed throughout the galaxy. It is a small noise, small intensity of noise, because the source of the galactic noise are located farther away from the sun. It is called as the black body noise. Okay. Man-made noise is due to the human activities. Okay. So for example, it's a spark producing mechanism such as commutators in the electric motors, automobile ignition, and etc. Impulse in nature contain wide range of frequency that propagate through the space at the same manner as radio wave. It is most intense in populated metropolitan and industrial areas, and it is also known as the industrial noise. Okay. Impulse noise. Impulse. If you see the impulse, impulse is like this. It is a it is a high amplitude of short durations. Okay, so this is supposed to be in term of time domain. So if we look from in term of time domain, it is something like this, impulse. It is a high amplitude of short duration. It is a high amplitude peak of short duration in the total spectrum. Okay, dia mempunyai masa yang pendek tetapi dengan amplitude yang besar. High amplitude, short duration. So this is a impulse noise. Okay, so it is produced from the electromechanical switches, electric motors, and etc. And then what? The last one is the interference. Interference is external noise which originate from the source that has the same frequency as our signal. Okay, interference is type of noise which is generated from a signal that has the same frequency as our signal. Okay. Internal noise, the noise that generated within the device or circuit. So that means this noise is generated within the transmitter or within the receiver. So there are three kinds of internal noise: short noise, transit time noise, and also the thermal noise. Okay, for example, the first one, short noise, it is caused by random arrival of carriers, which is the hole and electron within the device. Okay, at the output element of an electronic device such as diode, electric field effect transistor, or bipolar transistor. Okay, so this is the noise generated due to this random arrival of carrier within the device. Okay, so short noise randomly varying and superimposed into any signal present. So when amplified, short noise sounds similar to metal pellets falling on a tin roof. Sometimes it is called as the transistor noise. Okay. Transit time noise is due to the time taken for the carrier to propagate through the device in an appreciable part of the time of one cycle of the signal. So that means the time taken for the carriers to propagate within the device from input to the output. So these are categorized as transit time noise. The higher the time taken for the carriers to move from input to the output of the device, the higher would be the transit time noise. So this transit time noise is proportional to the time taken by the carriers to move within the device from input to the output. Okay, that means the higher the time of the movement, the higher would be the delay. Sorry, the higher would be the noise. Okay, the higher the delay, the higher would be the noise. Thermal noise. Thermal noise would be the main topic of chapter 2. Okay, it is due to the rapid and random movement of electrons within a conductor due to thermal agitation. and present in all electronic components and communication system. Okay, it present in all components within the communication system. It is uniformly distributed across the entire electromagnetic spectrum, often referred as white noise. White noise is not about color. Okay, the noise is not white color. Okay, white noise means that the noise is distributed across the entire frequency spectrum. So regardless of any frequency values, the thermal noise still exists. Okay, tak kiralah frekuensi apa pun, thermal noise itu tetap wujud. Okay, so thermal noise is independent of the frequency. Okay, regardless of what frequency, it still exists. Okay, so it exists in all frequency spectrum. So if you see from here, it is a temperature dependent, random and continuous, and occurs at all frequencies. Okay, and then what? Noise spectral density. The parameter is N0 or N0. Okay, so sorry, before that ada pelajar nak masuk tadi. Okay. Okay, so noise spectral density is the noise power per unit bandwidth. Okay, that means noise power divided with the bandwidth. Okay, watt per unit bandwidth, watt per hertz. Okay, so the unit is watt per hertz. Okay, dia adalah nisbah antara the ratio of power, noise power, divide with the bandwidth. Okay. Okay. So it has the unit of watt per hertz, which is equivalent to watt seconds or joules. Watt second or joules. So you can make the unit as a watt hertz or watt second or joules. Okay. So the noise is wide, constant with frequency, then the total noise power N in a bandwidth B is Bn0. Okay, so this N is the noise power. Okay, that means previously the noise spectral density, so this one I did a P, so it doesn't matter. So you see that from here, from noise spectral density, this one is equal to N noise power divide with the bandwidth. Okay, so therefore N0 multiplied with bandwidth, you're gonna get the noise power. Okay, so Bn0 would be the noise power. So this is underutilized in signal to noise ratio calculation. So we're gonna see later about this. The thermal noise density is given by N0 equal to KT. So another parameter to calculate N0, either you want to use a N over bandwidth or equal, this one is equal to KT. So there are two equations. The first equation is the above here, N over bandwidth. Okay, noise power. Okay, noise power divide with the bandwidth. This is the first one. Okay, second one is this one, K multiplied with T. Okay, K is the Boltzmann constant, K is the temperature in Kelvin. Okay, so remember, T is the temperature in Kelvin, K is the Boltzmann constant in terms of joule per Kelvin. Okay, so N0 is commonly used in link budgets as denominator of the important figure of merit ratios, EB over N0. EB is a bit energy divide with noise power spectral density. ES is the symbol energy per noise power spectral density. Okay, so what is this actually? Okay, both of these is the performance parameter that commonly used for the digital system. Okay, so both of these are equivalent, not the same, equivalent to the SNR in analog. Okay, in analog, we normally measure the performance of the transmitter and receiver in terms of signal to noise ratio. However, in the digital system, we commonly use both of these parameters to measure the performance of the transmitter and the receiver. Okay. Noise power, this is very important. Okay, noise power. So noise power is given as Pn or N equal to integral from minus bandwidth to the lower bound of bandwidth. Okay, lower bound of frequency bandwidth until the upper bound of frequency bandwidth. Okay, integral of N0 over 2 df. Okay, and you will get this one. Okay, N0 multiplied with the bandwidth. Okay, noise power spectral density multiplied with the bandwidth. Or you can use like this, KTB, because N0 is equal to KT. Okay, KT. So KTB. Okay, so this is important. So the unit for power is in terms of watt. And remember Boltzmann constant is this one, 1.38 multiplied with 10 power of minus 3. So this is a constant parameter. Bandwidth in terms of hertz. T is the absolute temperature in Kelvin. Make sure temperature must be in Kelvin. So how to convert Celsius to Kelvin? Okay, so Celsius to Kelvin, okay, degree Celsius to Kelvin, you need to plus, okay, you need to plus temperature in Celsius, you need to plus, for example here X Celsius, X Celsius, you need to plus with 273. Okay, then you will get parameter in terms of Kelvin. For example, like this one, 17 degrees Celsius plus 273. Okay, so you will get 290. 290 of what? Kelvin. Okay, so in your syllabus, in your lecture notes, okay, the ambient temperature is 17 degree, which is 290 Kelvin. Okay, ambient temperature or room temperature is considered as 17 degrees or 290 Kelvin. Okay, dalam kamu punya syllabus menggunakan 17 darjah as a room temperature, which is also equivalent to 290 Kelvin. Okay, so by default in your syllabus the room temperature is 290 Kelvin. Okay, so it is clear that the power spectral density of the thermal noise increase with the increase of ambient temperature. Therefore, keeping the electric circuit cool makes the noise level low. So you see that from this KTB, that means the noise temperature, the noise power is proportional to the increment of noise and also the bandwidth. The higher the temperature, okay, the higher the ambient temperature, the higher would be the noise power. Okay, ideally we want the noise power to be as low as possible. Okay, ideally we want the noise power to be as minimum as possible. Okay, that's the best case scenario. And you see that the noise power also proportional to the bandwidth. The bigger the bandwidth, the higher would be the noise power. Okay, that means we cannot use a very big bandwidth, otherwise the noise power would be increased. Okay, But in this topic, we want to focus on the temperature. Okay, so the temperature must be kept low in order to reduce the noise power. The lower the noise power would be better. Okay, lagi rendah noise power, lagi bagus. Okay, noise voltage. Okay, so noise voltage, if you see from here, from figure 2.4, shows the equivalent circuit of a thermal noise. Okay, so we have the noise source, this one, noise source, okay, connected to the load resistance. Okay, this is a load resistance. Okay, so you see that internal resistance is Ri. Okay, internal resistance Ri is connected in series with the RMS noise voltage Vn. Okay, so this is within the noise source. For the worst condition, okay, the worst condition means that that produce the highest noise. Okay, the load resistance R, okay, the load resistance R is equal to R internal of the noise source. So noise voltage drop across the load is half of the noise source. So that means the voltage drop, okay, when R equal to R internal, okay, when the load resistance equal to the internal resistance of the noise source, the voltage drop across the load resistance is half of the noise source. So this is considered as the worst case scenario. Okay, so that means you see that here VR or voltage at the load is equal to Vn over 2. Okay, so the noise power is Pn developed across the load. So power is Pn across the load, which is KTB, as we have measured in the previous slide. So from this KTB, we can define the noise voltage. Okay, so remember that here it is mentioned in terms of RMS noise voltage Vn. Okay, so from here you see that KTB is equal to, okay, this is the noise power at the load, noise power at the load equal to KTB equal to Vn square, Vn over 2 square over R. So this is the equation for power. Okay, remember power equal to V RMS square divide with 2, or you can say that this is V peak square divide with 2R. Okay, but in this case it is using the RMS, so V RMS square divide with 2. Okay, sorry, saya ulang wait, I repeat again. I repeat again. Okay, so power is equal to V RMS square divide with R, or you can say that power is equal to V peak square divide with 2R. Okay, since we are using a RMS voltage here, so that means we can use these equations. Okay, so how much is the voltage? The voltage during the worst case scenario, okay, this is defined during the worst case scenario. Worst case scenario shows the highest noise voltage. Okay, the highest noise voltage. Okay, so during the worst case scenario, Pn is equal to KTB, and then this is equivalent to Vn over 2. Vn over 2 is from here, the voltage drop at the load resistance during the worst case scenario. Okay, during the worst case condition. So Vrms is Vn over 2, so Vn over 2 square divide with R. Okay, which is this one. So this is equal to Vn square divided with 4R. Okay, and then we can rearrange the equations. Okay, so KTB equal to Vn square over 4R. So therefore Vn square is equal to 4R KTB. Okay, so this 4R can be bring forward. Okay, Vn square is equal to 4R KTB. So Vn is equal to square root of 4R KTB. So the unit is in term of volt. Okay, so this noise voltage is defined as the noise during the worst case scenario. Okay, the worst case condition. Okay, example. Calculate. So from here you need to do the calculations. So I think you will be happy after this, because we will do many examples, calculation examples. Okay, examples 2.2. Calculate the thermal noise power available from any resistor at room temperature 290 Kelvin for a bandwidth of 1 megahertz. Okay, so that means this is a T parameter, this is the B parameter. Calculate also. Okay, first the question asks noise power. How much is the noise power? Okay, and then calculate the corresponding noise voltage Vn. Okay, given R equal to 50 ohm. First find the noise power, which is a KTB. Okay, N equal to KTB. So it doesn't matter if you want to use N, you want to use P, or you want to use Pn, doesn't matter. Okay, as long as we know that this is the power. Okay, so noise power equal to K Boltzmann constant multiplied with the temperature 290 Kelvin multiplied with the bandwidth. So we get 4 times 10 power of minus 15 watt. Okay, so from here we can calculate the noise voltage, which is equal to 4 square root of 4R KTB. Okay, so since we already know KTB, we already defined in the previous question, which is this one. So we can just put inside this equation. So 4 multiplied with resistance multiplied with KTB and then square root. Okay, so we get 0.895 microvolt. Okay, you can try use your calculator whether you can get this answer or not. Okay, cuba guna calculator untuk pastikan jawapannya adalah betul. Okay, try yourself. Okay, so if you have question, please ask, no problem, I can explain again. Otherwise I will move to the next example. Okay, kalau ada soalan boleh tanya anytime. Example 2.3. For an electronic device operating at a temperature of 17 degree. Okay, so my advice, when you get temperature in terms of Celsius, straight away you need to convert into Kelvin. That means 17 plus 273. So you will get 290 Kelvin. Okay, remember, all temperature calculation in your syllabus will use the Kelvin temperature, not Celsius. Okay, ingat semua calculation in your syllabus, in this subject, if it is regarding the temperature, you must use Kelvin. Don't use Celsius. Okay, sometimes we give a question in terms of Celsius, and the students make a careless mistake. They use the 17 degree instead of 290. So the answer will be wrong. Okay, be careful. Okay, so this is the temperature T and bandwidth B is 10 kilohertz. Determine the thermal noise power in watts and dBm. And then determine the RMS noise voltage Vn for 100 ohm of internal resistance and 100 ohm of load resistance. So you see that if internal resistance equal to the load resistance, then this is going to be the worst case scenario, worst case conditions. So that means you can use the 4R KTB. Okay, normally we use only worst case scenario for the in the test and exam. Okay, okay, selalunya memang kita akan gunakan worst case condition. Okay, so and then what? So you see that during, if both of these equal, that means the voltage drop across the load is going to be Vn over 2. Okay, Vn over 2. So now we want to find, sorry, this is in order to avoid confuse, this is V over 2, voltage from the source divide with 2, like in the previous slide. Okay, so let's do the first question. Find the thermal noise power. So noise power N equal to KTB. KTB. So you will get 4.002 multiplied with 10 power of minus 17 watt. Okay. So how to calculate in terms of dBm? So dBm means that dB milli. So that means we need to divide the power with reference value 1 milli. And then we do 10 log. Okay, so we get negative 134 dBm. Okay, try use your calculator. Okay, so in this case, normally students also do a careless mistake. So what I suggest is that you need to do within this, you need to find the value inside the bracket first, then you do the 10 log. Okay, in order to avoid careless mistakes. Okay, and then what? Find the noise voltage. So the noise voltage Vn is equal to 4R square root of 4R KTB. So square root of 4 times resistance times KTB. So this is equal to 0.127 microvolt. Of course, in terms of RMS. Okay. If you have question, please ask. Otherwise, I will move to the next example. Okay. So you might ask, why we only use one resistance? Okay. This resistance is referring to the load resistance, not the internal. Okay. This is referring to the load resistance. Because if you see from the picture here, this is related to the load resistance, not the internal resistance. Okay, so that's why we only use 100. Okay, not the average. Okay, we only use the 100 load resistance. This one. Okay, not both. Okay, not both. So this equation, remember, for RKTB is related to the load resistance. Okay. Example 2.4. So you are given two resistors of 20k. This is R1, this is R2, 50 kilo ohm. At room temperature 290. So this is temperature. For a bandwidth of 100 kilohertz, so this is bandwidth. Okay, calculate the thermal noise voltage generated by, so there are three scenarios. Okay, so you have, remember you have R1 and also R2. Okay, so how much is the noise voltage for each of the resistor? So that means we need to find one by one. Square root of 4R KTB. Okay, square root of 4R KTB for R1, square root 4R KTB for R2. Okay, so here has the answer. So part A, question number A, so we need to find the noise voltage for each of the resistor. Okay, each of the resistor. So that means Vn1 is equal to square root of 4R1 KTB. Okay, so 4 times 20 kilo ohm multiplied with Boltzmann constant multiplied with temperature 290 Kelvin multiplied with 100 kilohertz of bandwidth. So we get 5.66 times 10 power of minus 6 volt. Okay, and then noise voltage 2 for noise voltage generated by the second resistance is equal to square root of 4R2, okay, 4 times resistance number 2 multiplied with the KTB. Okay, so 4 times 50 kilo ohm multiplied with 1.638 multiplied with room temperature multiplied with the bandwidth. So you get 8.95 microvolt. Okay, and then what? The question asks, what if the two resistors are connected in series? So that means, so both resistors are connected in series. So in this case, you need to find the total resistance, which is R1 plus R2. Okay, so if you see from here, okay, so the total resistance connected in series is 20 kilo ohm plus 50 kilo ohm, so you get 70 kilo ohm. So from here you can do the calculation, okay, using this R total. So V noise voltage is equal to square root of 4R total connected in series multiplied with K multiplied with T and B. Okay, so square root of 4 times 70 kilo ohm multiplied with Boltzmann constant multiplied with temperature multiplied with the bandwidth. So you get 1.06 times 10 power of minus 5 volt. Okay, and then what? Then the question says that the two resistors is connected in parallel. That means okay, so this is R1 and R2. Okay, so you need to find the R total. Okay, R total for parallel, I believe you already know about this. This is R2 and then inverse. Okay, so you can find the R total. Okay, here in the answer already given, okay, the R total is equal to 14.28 kilo ohm. Okay, 14.28 kilo ohm. So you can put inside the equation. Okay, so the total noise voltage for resistors connected in parallel, it is equal to square root of 4 times R total in parallel multiplied with KTB. So 4 times 14.29 kilo ohm multiplied with Boltzmann constant, the room temperature multiplied with the bandwidth. So you get 4.78 microvolt. Okay, so if you connected in series, you can get lower value of noise power or noise voltage. Okay, if you connected the resistor in term of parallel. Okay, kalau sambung secara parallel akan dapat noise voltage, lower noise voltage if you connect resistors in term of parallel compared to series connection. Okay, so if you have question, please ask about this. Okay, so this is A, B and C. Kalau ada soalan boleh tanya. Otherwise I will move to the next example. Okay, otherwise I will move to the next example. Okay, correlated noise. So this is the other type of noise. Remember, correlated noise is the type of noise that only present when there is a signal. Okay, it is not present if there is no signal. Okay, so this noise only present when there is a input signal, as I draw previously, that if, let's say, for example, a transmitter over here. So if, let's say, we have the input signal, then there gonna be some processes happen within the transmitter, and it will produce correlated noise due to this input signal. Okay, so correlated noise is divided into two in your syllabus, which is the harmonic distortion and intermodulation distortion. Okay, so the first one, so you see that this red color, this correlated noise will not present if there is no input signal. Okay, so correlated noise further divided into two categories, which are the harmonic distortion, HD, and also the intermodulation distortion. So the first one, okay, the first one, harmonic distortion, is unwanted harmonics of a signal produced through non-linear amplification or non-linear mixing. Harmonics are integer multipliers of the original signal. So the key word here is this one, unwanted harmonics of a signal. So that means we only have one input signal. Okay, one signal. Okay, one signal. One input signal. Okay, the keyword here is one input signal. Remember, input, we can have many inputs, or we can have single input. Okay, if the input is only one input, it will produce harmonic distortion. Okay, so what is harmonic? You need to know. Harmonic exists. Okay, the word harmonic. Harmonic is the small amplitude of noise. It's a small amplitude of signal that exists in the frequency spectrum. Okay, for example, this is your signal. If we see from the frequency domain, there is additional harmonics. Produced due to the nonlinear amplification. Okay, so this small signal, like we can see that this is a small signal, a small amplitude signal. It's an unwanted signal. Okay, it's an unwanted signal. So it is produced due to the mixing process, of the input and the, especially for the carrier. So it is either through non-linear mixing or through the amplification within the transmitter or receiver. Okay, so non-linear mixing or through the non-linear amplification, because inside the transmitter there's a amplifier. Okay, so these amplify the signal and it produce harmonics. Okay, so harmonics, there can be many harmonics, many small harmonics, small signal. Okay, the first harmonic, okay, the first harmonic is what we call as the second order. See, this is supposed to be HD. So please change your note. This is supposed to be HD, harmonic distortion. This is harmonic distortion. Okay, second order harmonic distortion is the ratio of RMS amplitude of the second harmonic to the RMS amplitude of the fundamental. Okay, and then third order harmonic distortion is the ratio of RMS amplitude of third harmonic to the RMS amplitude of the fundamental. So what is this actually? And let's look in this picture. Okay, I skip just to show this picture, picture A. Okay, picture A. So remember that the input is single signal. Okay, one input, single frequency. Put inside the system, what happened is that it produces harmonics. Okay, so originally is this input signal, and then it produces harmonics. So in this picture is up to first, second, third harmonics. Okay, so okay, sorry, in your notes it is called as a second order. So second order is this one. So this is the fundamental, the original frequency. Second order is the first harmonic after the fundamental. Okay, so this is a second order harmonics, third order, fourth order, and many others. Okay, so the fundamental frequency, normally sometimes it is called as the first harmonic, first order. Okay, but in this in your notes it is referring as the fundamental frequency, fundamental. Okay, then after the fundamental is the second order, third order, fourth order, and so on. Okay, how to calculate the second order harmonic? Second HD is equal to, okay, equal to V2 over V1 fundamental, and we normally multiply it with 100%, so we can get the value in terms of percentage. Similar with third order. Okay, for third order, third HD equal to V3 over V fundamental multiplied with 100%. Okay, and so on. Fourth order V4, fifth order V5, and so on. Okay, dan seterusnya. Okay, and then what? So we already look at the second order, third order, and also this one. Total harmonic distortion is the ratio of quadratic summation of RMS values of all the higher harmonics to the RMS value of the fundamental. Total. Okay, how to find the total harmonic distortion? Okay, so if you have for example like this until fourth order, okay, so you need to find, first you need to find, you see that this is the equation, this is the equation. Okay, this is supposed to be percent. So first of all, you need to find the V higher. V higher is the quadratic summation of the harmonics only. Okay, so for example here, first you need to find the quadratic summation. Okay, starting from the second order. So don't include the fundamental, no. You need to include only the harmonics. So second order, third order, until here in this example is until fourth order, so you can put V4. But in this equation is up to Vn, regardless of how many harmonics you have. Okay, until how many harmonics you have. If you have up to 10, then you can do up to 10. Okay, up to 10, V10 square. If you have until 10 order, that means V10 square. So after this, you can get the quadratic summation of the harmonics. Okay, and then what? You need to divide the quadratic summation voltage with the V fundamental. So that means you divide this with V1. Okay, so you divide this with V1. So the quadratic summation, okay, the quadratic summation divide over V1. So you will get the total harmonic distortion. So remember, after you divide, you need to multiply it with 100%. Okay, similar with this equation. Okay, V higher is the quadratic summation, V fundamental is a V1, and then multiplied with 100%. Okay, So we will see the example later about this. Okay. And then what? Okay. So the next part is the next type of correlated noise is the intermodulation distortion. Okay, intermodulation distortion is the generation of unwanted sum and difference frequency when two or more signals are amplified in a non-linear device such as large signal amplifier. So you see that here the keyword here is generation of unwanted sum and difference. When two or more signals, that means the input consists of two or more signals, not one. Okay, bukan satu. The input consists of two or more signals. Okay. So this is shown in the figure. Okay, in figure B. In figure B. So you see that we have two input. F1 and F2 with amplitude V1 and V2, and then put inside the system produce harmonics, which is what we call as the intermodulation distortion. So it produces unwanted sum and difference. What is unwanted sum and difference? Unwanted sum is the upper frequency harmonics, which is located at frequency F1 plus F2. Okay, the word sum here is referring to the frequency summation, the upper bound frequency, the upper bound harmonics. Okay, and the difference, okay, the difference is located at F1 minus F2. Okay, F1 minus F2. So this is the difference. Okay, V difference. Okay, and the original input is located at F1 and F2. Okay, so these two things is what we call as a V sum and V difference, and both of these is referring as the cross product. Kedua-dua ini dipanggil sebagai cross product. Okay, and for your information, in the real, in the practical system, in the real scenario, actually there are more harmonics over here. Okay, there are more harmonics, many small harmonics. Okay, but the main harmonic that we want to consider here is the sum and difference. Okay, because sum and difference has a bit higher in terms of voltage amplitude compared to the rest of the harmonics. Okay, so this distortion for the harmonic distortion and also the intermodulation distortion, so this disturbs the transmitted signal, the quality of the transmitted signal. Okay, kedua-dua ini harmonic distortion and also the intermodulation distortion disturbs the quality of the transmitted signal. Okay, ideally we want to reduce both of these. Okay, secara idealnya kita inginkan intermodulation distortion dan juga harmonic distortion itu seminimum yang mungkin. Okay, we want to minimize it or to eliminate it based on that certain frequencies using filters. Okay, so ideally we don't want this. Okay, ideally, okay, we don't want this kind of distortion, but this distortion always exists due to the signal processing. Okay, so as I mentioned previously that this one, both of these V sum and V difference, both of these are called as the cross product. So what is the cross product? Here the sum and difference frequencies are called the cross product. Okay, so figure B, we already see this figure B, and the cross product is measured as MF1 plus minus NF2. and the frequency of, then the first frequency f1 must be more than f2. Why? Because we don't want to produce negative frequency. Okay, don't produce negative frequency. Okay, because negative frequency does not exist. Okay, so you must make sure that f1 larger than f2 so that you are not producing negative frequencies. Okay, so f1 and f2 are the fundamental frequency. M and n are the positive integers between 1 and infinity. Any values between 1 and infinity. Okay, so we're going to see about this in the next example so that you can have more understanding about this intermodulation distortion. As I repeat that we try to reduce or eliminate the intermodulation distortion the best that we can, so that it will not disturb the quality of the transmitted signal. Okay, example. So let's do the example. So the first example 2.5. So this is example about harmonic distortion. Okay, this is about harmonic distortion. Okay, so the first question determine the second, third, and 12th harmonics for a 1 kilohertz of repetitive wave. Okay, so that means this is the F, and you need to find second, third, and 12th. Find the location of the harmonics. Okay, so the first question asks you to find the frequency location of the harmonic, second, third, and 12th. Okay, given the fundamental is 1 kilohertz. So how to do this? Okay, so you see that the first answer, question A, second order harmonic is located at 2 times the fundamental frequency, 2 times 1 kilohertz. So the second order harmonic is located at 2 kilohertz. Okay, di manakah lokasinya? So if you draw the frequency spectrum, so you have here fundamental at f1, okay, which is 1 kilohertz. Okay, and then the second order here, okay, which is this is v1, v2, located at f2, which is 2 kilohertz, and then f3, v3, which is located at 3 kilohertz, 3 times 1k, and then at 12th order, v12 located at f12, which is 12 times 1k, so it is located at 12 kilohertz. So these are the locations of the harmonics. Okay, we are not finding the distortion yet. Okay, the second question to find the harmonic distortion. Okay, so if you see the second question asks to find the percent of second order, third order, and total harmonic distortion for a fundamental frequency of with an amplitude of, so V1 is equal to 8 volt RMS, and then the second order is equal to 0.2 volt RMS. Third order is V3, which is 0.1 volt RMS. Okay, so if you see the A and B is not related actually. Question A and B is not related because question A, the question asks up to 12. Okay, so you might wonder why question B does not have up until 12. Okay, so it's actually question B is not really related to the first question. Okay, so what you need to find is the total harmonic distortion, THD, up to 3, up to the third order only. Okay, find total harmonic distortion up to third order only. Okay. So the question asks, what is the second order, what is the third order, what is the total harmonic distortion? The second order, okay, second order harmonic distortion is equal to V2 divided with the V fundamental multiplied with 100%. So you get, so V2 is 0.2 volt divided with 8 volt multiplied with 100%. So you get 2.5%. Okay, third order harmonic distortion is equal to V3 divided with V1 multiplied with 100%. So 0.1 volt RMS divided with 8 volt of fundamental frequency multiplied with 100%. So you get 1.25%. So you get a percent of second order, percent of third order. Now find the percent of total harmonic distortion. So that means first you need to find the quadratic summation, which is the V higher. So this one, so quadratic summation of V2 square, second order, plus with 0.1 square of third order. Okay, second order voltage square plus third order voltage square divide with fundamental V1 multiplied with 100%, so you get 2.795%. Okay, so in this case you need to read the question up to which harmonics that the question wants. Okay, you need to read the question so that you can understand that up to which order. Okay, the question should clearly state up to which order of harmonics that you need to calculate for the total harmonic distortion. In this example, it is mentioned up to third harmonic. Okay, if the question asks until 10, for example, then you need to calculate until 10 order. Okay, so any question you can ask, otherwise I will move to the next example. Okay, kalau ada soalan sila tanya, no problem, boleh tanya. Okay, the next example, example 2.6. So this is about intermodulation distortion, ID. Okay, intermodulation distortion. So for a non-linear amplifier with two input frequencies, so the keyword here is two input. Okay, so the first one is here 3 kilohertz F. So F 3 kilohertz and 8 kilohertz determine. Okay, so as the first three harmonic, because we want to find the cross product. Okay, because we want to find the cross product, so therefore you can state that. So I go back first. I go back to previous slides. You see that we can assign F1 to be the higher frequency compared to F2, so that we are not produce a negative frequency, because negative frequency does not exist. Okay, so in this case I will put here F1 and this is F2. Is it? Okay, it doesn't matter, F1 and F2. Okay, so the question asks the first three harmonics present in the output of each input frequency. So the first question asks the location of frequency of the harmonics. Okay, the location of the harmonics in terms of frequency. Find the location and then find the cross product for value of M and N equal to 1 and 2. So here you will see later that be careful about this. So this is actually M equal to 1 and 2, N equal to 1 and 2. Okay, in this example. Okay, so we're gonna see this later about this. So the first question, the location of the harmonic. Okay, the location of the harmonic. So each frequency will produce harmonics. Okay, harmonics produced by the 3 kilohertz frequency. You see that the first here, first harmonic or the fundamental. Again, some literature book use first harmonic, some other literature book use fundamental frequency. Okay, so this is the fundamental. Okay, which is 3 kilohertz. Of course, the original frequency input. Okay, second order is located at 2 times original signal frequency. So 2 times 3, so you get 6 kilohertz. Third order, 3 times original frequency, so 3 times 3, so 9 kilohertz. So these are the locations of the harmonics produced by this input 3 kilohertz. What about frequency 8 kilohertz? 8 kilohertz also produce harmonics. Okay, so the first order harmonics or the fundamental is equal to 8. Second order, 2 times original frequency, 2 times 8, so we get 16. Third order, 3 times 8, so you get 24 kilohertz. Okay, so these are the location of second order and third order harmonics. Okay, so if you draw the frequency spectrum, we have the V sum and difference. So actually we have another frequencies over here, another harmonic, small harmonics, okay, produced due to the nonlinear amplification. Okay, so how to do this? So since we have M and N both equal to 1 and 2, okay, both equal to 1 and 2, okay, so that means we need to do a table so that we can find one by one. So that means we're gonna have a 4 combination. We're gonna have 4 combination, okay, which is like this. Okay, so for example, when M equal to 1, N equal to 1, so the cross product is, remember the cross product is MF1 plus minus NF2. Okay, so that means 1 and 1. So 1 and 1, so that means F1 is equal to 8 kilohertz, F2 is equal to 3 kilohertz. This is from the question, okay, from the given question. Okay, so therefore it is 8 plus minus 3, so we get 5 kilohertz for the V difference and 11 kilohertz for V sum. Tambah hasil tambah and hasil tolak. Okay, so this is 8 minus 3, 8 minus 3 you get 5, 8 plus 3 you get 11. Okay, second row, M equal to 1, N equal to 2. Okay, so that means 1 times 8 plus minus 2 times 3, which is 6. Okay, because N is equal to 2, so 2 times 3 you get 6. So 8 plus minus 6, so we get 8 minus 6, we get 2 kilohertz. 8 plus 6, we get 14 kilohertz. Okay, and then M equal to 2, N equal to 1, so that means 2 times 8 kilohertz, which is 16. 1 times 3, we get 3 kilohertz. So therefore the sum and difference, the difference is 16 minus 3 kilohertz, so we get 13. V sum is equal to 16 plus 3, so we get 19 kilohertz. Okay, and then what? M equal to 2, N equal to 2. So 2 times 8 we get 16, 2 times 3 we get 6. So 16 minus 6 we get 10 kilohertz for difference. 16 plus 6 we get 22 kilohertz for the V sum. Okay, so So do you have question to ask about intermodulation distortion? Ada soalan nak tanya, boleh tanya. Please ask question.
Doktor,
Ya.
macam mana kita nak tahu susunan M dengan N tu, macam M ni 1122 kan? N 1212, memang macam tu ke?
Macam mana nak tahu susunan dia? So kita start daripada we start with the lower value. Okay, we start with the lower value M1 and then N1, N2. So we start with lower value.
Okay.
Kita mula daripada nombor yang rendah.
Okay.
Okay. Lagi. So because if you have two combination, they're going to be 2 power of 2, which is 4. They're going to be 4 combination. Okay, so 1 and 1, 1 and 2, 2 and 1, 2 and 2. So you start with the lower value, 1. 1, and then 1 and 1, 1 and 2, and then if you have 3, 1 until 1 and 3, something like that, okay? So in the previous semester, we have asked this question a long time ago. Few semesters ago, we have asked this question where we use M and N 1 and 2. Okay, up until now we use the same M and N in the example. So during the test or final, we will use the same 1 and 2. Okay, so don't worry about that. Jangan risau. Okay, so the keyword here is we start with the lower M and lower N values. Okay, start daripada nilai yang rendah 1, kemudian 2. Okay. And then any question? Any other question? Ada lagi soalan? So if you don't have question, then I will move to the next topic. Okay, tak ada soalan Kalau tak ada, then I will move to the next topic. So the signal to noise ratio. Okay, betul tak ada soalan Okay, kalau tak ada saya teruskan. Okay, signal to noise ratio SNR, or sometimes we write S over N, which is the ratio of signal power divide with the noise power. Okay, signal power, so divide with the noise power, so it is watt divide with watt. Okay, S over N is equal to power of the signal divide with power of the noise. So both watt over watt, so you will get a value without a unit. So this is a unitless parameter. Okay, SNR is a unitless parameter, and we can represent it in terms of decibel. So 10 log power ratio. Okay, 10 log power ratio in terms of decibel. Okay, so SNR is one of the performance parameter to check the quality of the transmitted signal. We want to know how much is the power of the transmitted signal over the noise power. Ideally, we want SNR to be as maximum as possible. Okay, kita inginkan nilai SNR ini sebesar yang mungkin. Why? Because we want this signal power to be much larger than the noise power. Okay, so therefore, the higher the SNR value, the better would be the quality of the transmitted signal. Because the noise, if the SNR is higher, that means the signal power is much stronger compared to the noise power. Okay, and in practical system, normally we measure the SNR in terms of decibel, dB. Okay, and we can also see the SNR in terms of voltage and power ratio. Okay, so remember that power is actually V square over R, which is this is RMS, or you can write V square, V peak square over 2R. Okay, so this is the power. So if you put inside the equations, okay, okay, for example, I'm using the RMS. For example, contoh so this is actually 10 log, for example, I'm using the RMS, so Vs square divide Vs square divide with R divide with Vn square divide with R. Okay, so this is equal to 10 log Vs over Vn square. So you're gonna get 20 log Vs over Vn. Okay, so 20 is not the magic number. Okay, 20 ini bukan magic number. Okay, so if you are okay, so during the test or exam, when you want to find the voltage of signal or voltage of the noise from a given decibel value, so you need to use a 20 log like this. Okay, don't use 10 log, otherwise you will produce a wrong answer. Okay, because this is a voltage ratio. Okay, remember in chapter 1, a few slides at the end shows about the decibel for power, for ratios, power ratio, voltage ratio, and current ratio. Okay, it's similar for current. Current also use 20 log of Is over In. Okay, so that one is for the current. Okay, example, let's do example. Example 2.7. For an amplifier with the output signal power, so you have amplifier like this. Okay, output signal power, which is you can say that PS. Okay, and also this is 10 watt. Okay, or you can and then this is PN, power of noise output. Okay, at the output side, which is 0.01. Determine the SNR. So SNR is equal to noise power, signal power over noise power, 10 watt divide with 0.01 watt. So you get 1000. Okay, and then in terms of decibel, 10 log 1000, you get 30 decibel. Okay, so class unitless, you don't need to write like this. Okay, in exam or test, you don't need to write unitless. No need to write the word unitless. Tak perlu tulis unitless. Just write the value like this, 1000. So we understand that this is a unitless parameter. Okay, otherwise it will looks funny. So if you write unitless, okay, you give the answer and then suddenly there's a unitless. Okay, so if unitless, that means no unit. Okay, so in terms of decibel, 10 log 1000, so you get 30 dB. So you see that the question doesn't specifically ask you to find decibel. Okay, the question does not explicitly ask you to find decibel. So actually you can stop until here. Okay, but unless the question asks explicitly you need to find in terms of decibel, then you need to proceed until decibel. But a good practice is to find in terms of decibel for the SNR, because in the real world scenario, in the practical case, in the practical scenario, we normally mention the SNR in terms of dB. Okay, biasanya SNR ini disebut dalam sebutan decibel. Okay. Example 2.8. If you have question, please ask. If you don't have, then I will move to the example 2.8. Example 2.8, for an amplifier with an output signal voltage of 4 volt. Okay, this is Vs. Okay, and output noise voltage, this is Vn, and input and output resistance of 50 ohm. Determine the SNR. Okay, so SNR is equal to Vs square over R divided with Vn square over R, or you can say that this is, you can cancel out the R, so this is 4 square divided with 0.005 square, so you get 640,000 no unit. Okay, and in terms of decibel, it is equal to 10 log 640,000, which is 58 dB. So you see that the good thing about using decibel is that we can change the big value like this, 640,000, to become only 58. This is the beauty of decibel. Okay, the good thing of using the decibel, easy to do the calculation. Nampak nilai yang besar ini telah ditukar kepada nilai yang lebih kecil dalam decibel untuk memudahkan pengiraan. Okay. So if you have question, please ask. Otherwise, I will move to the next example. Okay. Otherwise, I will move to the next example. So you might wonder why we don't use 20 log. Because we already get the value here. We already get the value of SNR. We just need to convert it. Okay. If you use 20, you can use like this. It's actually like this: 10 log 4 square. So like this. Okay, 4 divided with 0.005 square. So it is actually like this. So 20 log 4. Okay, so you will get 58 dB. Okay, you will get 58 dB. Okay, ada soalan? If you have question, please ask. Otherwise, I will move to the next example. Okay. Kalau tak ada soalan, saya teruskan. Okay, noise factor and noise figure. This is the main topic in chapter 2. Okay, this sure will come out in your test and final exam for sure. Dia akan keluar dalam test dan juga final exam. So noise factor is equal to input SNR divide with output SNR. Okay, so SNR input divide with SNR output. Okay, input over output, not output over input. Jangan salah. Don't do careless mistakes. This is about SNR input over SNR output. So what is SNR input and output? Okay, if you see an amplifier system, if you remember amplifier system, we have input and output. Okay, so over here we have the, for example, P in and P out. Okay, and here we also have the sorry, I changed the parameter. Wait. Let's do in terms of S. Okay, so we have a input signal, we have the output signal. Okay, so this is in terms of power. So we have an input power and also the output power. We also have the input noise and output noise. Okay, so both of these at the input produce input SNR. Okay, SI over NI is equal to the input SNR. So this is NI. Okay, this is the input SNR. Output SNR SO, output signal power divided with output noise power. So this is the output SNR. Okay, so this is the SNR I, this is the SNR O. Okay, so that means this is SNR I over SNR O. And then what? Noise figure. Noise figure is 10 log F. Okay, 10 log SNR I over SNR O. Okay, in term of, we get the value in term of decibel. So 10 log F. What is F? F is this one, F. Okay, 10 log noise factor. 10 log noise factor, you will get noise figure. Okay, F noise factor is just a ratio. There's no unit. It's a unitless. Noise figure has parameter, which is dB. Okay, for a perfect, you see that for a perfect noiseless circuit, F equal to 1. That means output SNR equal to input SNR. So perfect system, noiseless. Okay, F equal to 1. So therefore, an F noise figure is 10 log 1. 10 log of 1, you get 0 dB. This is for a perfect system. Remember, the value of F, we want the value of F to be as minimum as possible towards 1. Minimum is 1. Okay, that means output equal to the input. The ratio, the ratio is output SNR output equal to the SNR input. Okay, so it is F equal to 1. Remember, we want the noise factor to be as minimum as possible. Kita nak noise factor ini sekecil yang mungkin. Okay, the lower the noise factor, the lower would be the noise within the system. Okay, we don't want this actually. We don't want the noise factor actually, because this noise factor disturbs the system. Okay, so remember, perfect is 1. Normally you will see later that the value is more than 1. Okay, normally in practical cases the value is more than 1. Okay, we want the value of F towards 1. Okay, kita nak nilai F ini menuju nilai 1. Okay, so this is the equations for the perfect system and non-perfect system. What's the difference actually? So in order to understand this, we need to see the picture, this one. Okay, we need to see this picture to understand the equation. Okay, so let's look at the above picture. So you need to understand this. So we have this is the above picture is a noiseless amplifier, perfect system. Picture B is a non-ideal amplifier which generate internal noise. Okay, so let's look at picture A. Okay, so we have the input signal power, we have the input noise power. Put inside the amplifier. Amplifier has a gain of AP, power gain of AP. And this amplifier is a noiseless amplifier. Means that this amplifier does not produce additional noise within the amplifier itself. Dia tidak menghasilkan additional noise di dalam amplifier itu. Okay, so that means the noise is not from the amplifier, it is from the outside. Okay, so the amplifier is noiseless. It does not produce additional noise. Okay, it only consists of gain only. Okay, so therefore the output signal power is equal to AP multiplied with the input signal power. Okay, APSI. Okay, remember about gain. If you remember gain, okay, so we need to multiply. We need to, for example, we have a PI here, we have the A here. We have a PO here. Remember that PO is equal to A multiplied with PI. Remember this? So it is similar with this one. So you need to, in order to find the output power, you need to multiply the input power with the gain. Okay, similar with the output noise power, which is gain multiplied with the input noise power. So what happened is that we can cancel out the gain like this. So finally you will get SI over NI, which is similar with, which is the same as SI over NI at the input. In terms of ratio, it is same. Okay, so this one SNRO, okay, SNRO and also SNRI is equal. Okay, so that means SNRI is equal to SNRO. Okay, so you get SI over NI. So this is F equal to 1 and F equal to 0 dB. Okay, 10 log 1 you get 0 dB. So this is a perfect system. The amplifier does not produce additional noise. Okay, so let's look at the picture B. Okay, picture B, non-ideal amplifier. Okay, so you see that here the input signal power is SI, input noise power is NI. So it will produce a SNR input. Okay, so within within the amplifier, it has a gain of AP, and it also produces internally generated noise, ND. So this amplifier produce additional noise, which is ND. Okay, normally it is produced due to the high temperature within the amplifier. So it produces internally generated noise. So what happened at the output? The output signal power S out is equal to gain multiplied with input signal power, APSI. Okay, what happened to the output noise power? So you see that N out, output noise power is equal to AP gain multiplied with input noise plus additional noise produced by the amplifier. Okay, so if you cancel out, if you divide with AP, so you get like this, this one. Okay, so in this case, you will see that SNRO is less than SNRI. Okay, that means the value of F larger than 1. Okay, the value of F larger than 1. Okay, so this is the non-ideal case. Okay, so this is for the single amplifier. What if, okay, what if we have many non-ideal amplifier? Macam mana kalau kita ada banyak non-ideal amplifiers? How to find the noise factor? How to find the noise factor? Okay, like this. Okay, for example, here you have 3 cascaded amplifiers like this. So how you want to find the noise factor? Total noise factor. How? Okay, so in order to find the total noise factor for a cascaded amplifier system, you need to use the Friis formula. Okay, to calculate the noise factor, total noise factor. Okay, so Friis formula, you see that here F total equal to F1. Okay, so here is F1 noise factor due to the first amplifier plus noise factor due to the second amplifier minus 1 divide with gain from the first amplifier plus noise factor from the third amplifier minus 1 divide with gain from the first and second amplifier. Okay, until Fn. Okay, until Fn. So noise factor of n amplifier minus 1 divide with the total gain from the first until the previous amplifier. Okay, so for example, for the 3 cascaded system like this, for example, okay, for example, you have 3, you have 3, for example. Normally we ask up to 3 in the exam, normally. Okay, we don't ask until 4 and more than that, no. Normally we ask until 3. So this is 1, 2 and 3, okay. So we have F1, we have F2, we have F3, okay, and we have A1, A2, A3, okay. So therefore you want to find the F total is equal to noise factor of the first amplifier plus noise factor of the second amplifier minus 1 divide with the gain from the previous amplifier plus noise factor of the third amplifier minus 1 divide with the total gains of previous amplifiers, which is A1 multiplied with A2. Okay, so you get the F total. From F total, okay, from F total you can find the noise figure, okay, which is NF total is equal to 10 log F total. So you get in terms of decibel. Okay. Normally before the previously before the pandemic, COVID pandemic, when we did the final exam in as a face-to-face in the exam hall, we give the formula. Okay, we give the formula inside the question, so you don't need to memorize too many equations. However, during the COVID pandemic, because we will do the exam online, so we don't give the equation, so you can find from the notes. Okay, so this is the example up to 3 cascaded amplifiers. Okay, and you see that so I already explained about this. Notification, this is very important. Change unit of all noise factor and power gains A from dB to unitless before insert into the Friis formula equation. Students always do careless mistakes in this part. Okay, remember, okay, remember all values within this formula, all values inside here must be in terms of unitless. Don't put decibel parameter inside the Friis equation. Be careful. Okay, pastikan semua parameter di dalam Friis equation ini is in terms of unitless. Okay, that means gain in terms of unitless, F also unitless. Don't put decibel. Okay, everything inside this equation must be unitless. Don't put decibel parameter inside this equation, otherwise you will produce the wrong answer. Okay, be careful. Okay, saya dah ingatkan banyak kali. I already remind you many times. Okay, make sure that all parameters inside the Friis equation must be unitless parameter. Don't put decibel parameters inside the Friis equation. Okay. Okay, let's do example so that you can have more understanding about this. Okay, so the input signal to a telecommunication receiver consists of 100 microwatt, okay, of signal power and 1 microwatt of noise power. So for example, here we have a telecommunication system. We can just draw a box like this. So the input is 100 micro is given, SI is 1 micro, NI is given as 1 micro. Sorry, this is 100. 100 micro and 1 micro. Okay. So the receiver contributes an additional 80 watt of noise. So ND produced internally by the system is equal to 80 micro. Okay. And it has a gain of 20 dB. A is equal to 20 dB. Okay. What's the question? So the question asks, compute the output, compute the SNR input, SNR output, and receiver noise figure. So we don't know how much is SO. We don't know how much is SO. We don't know how much is NO. And we want to calculate how much is the SNR. Okay, SNR O. And also we want to find the SNRI. SNRI is easy to find. Okay. So compute the SNR. Okay, SNR input is equal to, first you need to find a SI over NI. So 100 micro over 1 micro, you get 100. Then do the, in terms of decibel, 10 log 100, so we get 20 decibel. So this is the input SNR. What about the output SNR? Output SNR, first of all, you need to find SO, you need to find NO, then you can find the output SNR. Okay, so in order to find the output SNR, I would suggest you to find the output signal power first, because it is easy. Okay, output signal power is equal to AP, gain multiplied with input signal power, so 100. So how come this is 100? 100 here is from 20 dB. Remember the question gave 20 dB. So anti-log of 20 dB is 100. So how to do this? You can do the anti-log of 2. Okay, use your calculator. Why I use anti-log of 2? Because 10 log x is equal to 20 dB. Okay, log x is equal to 2 dB. Okay, because we divide with 10. So x anti-log of 2, so we get 100. Okay, how to do anti-log? Shift log. Okay, shift log 2, you get 100. Okay, so gain multiplied with 100 microwatt of input, so we get 1 times 10 power of minus 2 watt. Okay, and then the output noise. Output noise is equal to internally generated noise plus NO. NO is gain multiplied with input noise. So therefore 80 micro internally generated noise plus gain multiplied with the input noise. So we get 1.8 multiplied with 10 power of minus 4 watt. Okay, so from here we can find the SNR. SNR O is equal to S out divide with N out. So it is equal to 1 times 10 power of minus 2 divide with 1.8 times 10 power of minus 4. So we get 55.56. In terms of decibel, 10 log 55.56, so we get 17.45 decibel. Okay, so we get the value in terms of decibel. And then what? Okay, So the third question asks, how much is the noise figure? How much is the noise figure? Noise figure is equal to 10 log of f. Okay, so 10 log of f. So this is actually 10 log of 100 input SNR. Input SNR we already get 100, this one, divide with output SNR, which is this one, okay, 55.56, okay, 55.56. So you get 2.55 decibel. Okay, another way is to do the to find the difference between two SNR. You see that here, NF, so NF is equal to, you can do like this, SNR I, sorry, another method, this is in terms of dB, is equal to SNR I in terms of dB minus SNRO in terms of dB. So this is equal to 20 minus 0.17.45. Okay, so 20 okay, 20 minus 17.4, so 2.55. Now, easy, okay, simple. Okay, if you have question, please ask. Kalau ada soalan boleh tanya. You can ask. Otherwise, I will move to the next slide. Okay, kalau ada soalan boleh tanya. Otherwise, I will move to the next slide. Okay, ada? So if you don't have question, I will move to the next example. Ada soalan ke? Tak ada. Okay, example 2.10. For a non-ideal amplifier and the following parameters. So you are given input signal power SI, given input noise power NI, you are given A, you are given ND. Okay, find the SNR in terms of dB, output SNR dB, noise factor and noise figure NF. Okay, input SNR is easy, 10 log of SI over NI. Okay, you see that here, SI over NI, 2 times 10 power of minus 10 divide with 2 times 10 power of minus 18, and then we get 1 times 10 power of 8, and then find the decibel 10 log of 100, this one, okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we get 80 dB. Okay, and then the output noise power, I suggest you to find S out first. S out, output signal power is equal to gain multiplied with input signal power. So gain is 1 million, given in the question. The question gave 1 million. Multiplied with the input signal power. So you get 2 times 10 power of minus 4 watt. Okay. And then the output noise power is equal to internally generated noise plus gain multiplied with input noise. So internally generated noise, 6 times 10 power of minus 12 watt plus this one gain multiplied with input noise. So you get 8 times 10 power of minus 12 watt. Okay, so from here you can find the output SNR. Output SNR is equal to 10 log of this, 2 times 10 power of minus 4 divided with 8 times 10 power of minus 12. Okay, so how much is this? 2 exponent minus 4 divided with 8 exponent minus 12. So you get 25 million. So 25 million. Okay, 25 million. So it is actually 73.979. Okay, so it is rounded up to 74. Okay. Then what? Noise factor. So noise factor is equal to, so 1 power of this is an input SNR, 1 times 10 power of 8 divide with 25 million, so we get 4 noise factor. Noise figure is equal to 10 log of noise factor, which is 6.02 dB. Okay, so decibel of noise factor is noise figure. So 10 log 4, you get 6.02 dB for the noise figure. Okay, so this is a straightforward question. So you have question to ask about this example. Boleh tanya, you can ask. If you have question about this example, please ask question. Yeah, so no question. If no question, then let's look the next example. Okay, let's look the next example. Example 2.11. Example 2.11, this is for a cascaded amplifier. Okay, for 3 cascaded amplifier, 3. So that means we have 3. So I suggest you to draw. Okay, so each noise figure is 3 dB and power gains of 10 dB. Determine the total noise. So 1, 2 and 3. So this is so I make it bigger. So 1, 2 and 3. Okay, so you are given all amplifiers has the same values. In this example, all amplifiers has the same noise figure and the same gain. So that means NF1 is equal to 3 dB, NF2 is equal to 3 dB, NF3 is equal to 3 dB. And then gain. So the gain is A1 is equal to 3 dB, A2 is equal to 3 dB, A3 is equal to 3 dB. Okay. So the question asks, how much is the total noise figure? How much is the total noise figure, NF total? In order to find NF total, first of all, you need to find F total. In order to find F total for a cascaded system, you need to use the Friis equation. Remember, Friis equation, we need to use unitless parameter, not decibel. So what we can do is that we need to do the anti-log for all the parameters. For example, here, this example, do the anti-log for the gains. Okay, anti-log of sorry. Oh, saya silap sikit Wait. Okay. Why nobody notice about this? This is supposed to be 10 dB, not 3 dB, 10 dB. Sorry, 10 dB. Okay, so the noise figure 3 dB, power gain is 10 dB. Okay, so in order to use the Friis equation, we need to find the parameter in terms of unitless. So the gain in terms of unitless is equal to A1 equal to A2 equal to A3 equal to antilog of 10 dB. Okay, antilog of 1 you get 10. Okay, antilog of 1 you get 10. So try use your calculator. 10 divided with 10 you get 1. Antilog of 1 you get 10. Okay. And then what? Antilog of 3 dB for the noise figure. In order to find the F, antilog of NF you get F. F1 equal to F2 equal to F3 equal to antilog of 0.3. 3 divide with 10 and then do the antilog. Okay, so antilog of 0.3, it is 1.995. In this example, it has been rounded up to 2. So that easy for you to understand. Okay, so once you already get the value in terms of unitless, then you can find the total noise factor using the Friis equation. Okay, so therefore the total noise factor of the first amplifier plus noise factor of the second amplifier minus 1 divide with the previous gains A1 plus noise factor of the third amplifier minus 1 divide with the total gains of the previous amplifiers, which is A1 multiplied with A2. Okay, so here we can do 2 plus 2 minus 1 over 10 plus 2 minus 1 divide with 10 power of 10. The gain for the first and second. This is the gain for the first amplifier, and this is the gain for the first and second amplifier. Okay, so you will produce 2.11. Okay, from here you can find the NF total, which is 10 log of 2.11. So you get 3.24 decibel. Okay, so this example, all amplifiers has the same value. Okay, has the same value. All amplifiers have the same value, so therefore you are given the value in terms of decibels. So you need to find the unitless parameter. Then you can determine the total noise factor. Then you can find the total noise figure. Okay. Any question you want to ask? Ada soalan? Okay, the next topic is about noise equivalent temperature. Okay, equivalent noise temperature, which is TE. Okay, so again, from the original equations of noise power, which is KTB, we can define the equivalent noise temperature TE. So TE is a hypothetical value that cannot be directly measured. Convenient parameter often used, it is also indicate the reduction in the signal to noise ratio a signal undergoes, it propagates through a receiver. So the lower the TE, the better would be the quality of the receiver. Okay, so TE is the internally generated temperature, okay, because of the process happens inside the device. Okay, so TE is range from normally range from 20 Kelvin until 1000 Kelvin for noisy receivers. So mathematically, TE is equal to T multiplied with F minus 1. Okay, so you need to understand about this equation. Okay, so TE is the equivalent noise temperature in Kelvin. T here is the environmental temperature. Okay, by default is 17 degrees Celsius or 290 Kelvin. Okay, F is the noise factor, unitless. Okay, if you rearrange the equation, you can find F equal to 1 plus TE over T. Okay, if you rearrange the equation, you will find this. Okay, so TE in term of Kelvin, okay, TE is in term of Kelvin, F no unitless parameter. Okay, example, so let's do the example. Determine the noise figure, okay, determine the noise figure for an equivalent noise temperature of 75 Kelvin. So you need to find NF. Before you find NF, you need to find the F. Okay, F is equal to, so you are given TE. So 1 plus TE over T. Okay, F equal to 1 plus TE over T. So TE is given 75 Kelvin. T is the ambient temperature or room temperature, which is 290 Kelvin by default. Okay, by default in your syllabus, room temperature is 290 Kelvin or 17 degrees Celsius. Okay, so you get 1 plus 75 TE over room temperature, so you get 1.258. From here you can find the noise figure, which is 10 log of noise factor. So you get 1, approximately equal to 1. Okay, so 10 log 1.258, so it is actually 0.996806, so rounded up to 1 dB. Okay, noise, and then the second question, okay, second question said that find the equivalent noise temperature, find the TE if you are given the noise figure equal to 3 dB. Okay, so from noise figure you need to find F. How much is the value of F? Okay, because you want to find a TE. TE is equal to F minus 1. Okay, so you need to find the F. So F is antilog of 6 dB. Okay, 6 divided with 10, 0.6. So antilog 0.6, you get, sorry, noise figure 10. Oh yeah, antilog of okay, antilog of 0.6, you get 3.981, so it is rounded up to 4, so no problem. From here you get F, and then you can find the TE. TE is equal to T multiplied with F minus 1. So you get 290 multiplied with 4 minus 1. Okay, 4 from here. Okay, so you get 870 Kelvin. Okay, so you see that the second question used this equation. Okay, the first question used this equation. So you need to understand the relationship between noise factor and also the equivalent noise temperature, TE. Okay, you need to understand the relationship between F and TE. Okay, so in this second question we do the antilog because we want to find the F, noise factor. From there we can calculate the equivalent noise temperature. Okay, any question? Student, are you still there? Any response? Boleh siapa-siapa
Yes, doctor.
Okay, thank you for the response. Sometimes I'm afraid that I talk to myself. because when I open the slide I cannot see you. Okay, so so luckily you are still there, so I'm not talking to myself. Okay, so if you have question, please ask, no problem. Otherwise we can move to the next slide. Okay, siapa penat boleh relax. If you feel tired, you can relax. You can have a break on your own. I will proceed as usual. Okay, noise measurement. Okay, noise measurement is related to the RMS noise voltage. Okay, so to work with the noise communication system, it must be measured in a meaningful way. So noise is a random process and does not have a single value or an equation to describe it. The root mean square value of the noise is the most important fact. RMS value is formed by taking the square root of the average of the individual noise voltage which have been squared. Okay. So in order to find the root mean square of noise voltage, for example, here we have the 10 values of measured noise. Okay, 10 noise voltage values that has been measured using the voltmeter. Okay, so in here we have the 10 values. This is example which consists of 10 values of measured noise voltage. So the noise is measured using equipment which is for example like the voltmeter, for example, to measure the noise. And then from here we need, first of all, the first process is we need to find the summation of root means quadratic summation. Okay, first we need to find the quadratic summation of all the voltage readings. Okay, so we found the quadratic summations. Okay, so since we have 10, so we do the quadratic summation for all the values. So we get 3.0325 volt square. Okay, and then what? The second process is to find the average from the quadratic summation. Okay, so from here, quadratic summations divide with 10. Why 10? Because we have 10 values. Okay, we have 10 voltage readings. If we have 100 values, then we need to divide with 100. If we have 20 values, then we divide with 20. So in this example, we have 10 values. So we divide with 10. Average of the quadratic summations. Okay, and then what? The last process is to find the square root. Okay, square root of the average. This one. Okay, this is from this one. Square root of the average, we get 0.55 volt. So this is the RMS voltage value of all the voltage readings. Okay, another example. Okay, another example, also 10 values of RMS noise voltage. Okay, so we have 10 RMS noise voltage readings. Okay, 10 meter readings. So we have 10 volt, 100, minus 100 volt, 35 volt, and until minus 20 volt. How much is the RMS noise value for all of the readings? Okay, first find the quadratic summation. Okay, so we get 24,751 millivolt square. Second process, find the average. So quadratic summation values divide with total number of values. So we have 10 values. So therefore we get 2471.1 millivolts square. Okay, and then what? The third process is to find the RMS value. We do the square root. Okay, so square root of this. Okay, square root of 2475.1. Square root of this, you will get 4975. Okay. Okay, square root of 2475.1. Okay. So you get 4975 millivolt for the RMS noise value. Okay, so that's all. Do you have question? Ada soalan tak nak tanya? Do you have question to ask? Do you understand? If you don't understand, I can explain again. No question? Betul tak ada soalan Okay. Okay. Before we, maybe I want to show you previous semester test question. Okay, I want to show you previous semester test question. Okay, before we end this, maybe we can do one example. So I know that you are feeling tired, especially for the Muslim. We are fasting today. Okay, of course we feel tired. Kalau you rasa mengantuk, saya yang mengajar ni pun lagi penat sebenarnya. But I try my best to teach you during the fasting hours. For 3 hours, so no problem for me. Okay, so let's try to do example. This one. Okay, you can get this from the question bank. Okay. If you go to the test 1 folder, okay, go to the test 1 folder, you can find this question from the question banks. Okay, pergi kepada test 1 folder, you can find this question. Okay, so this is a long time ago. Okay, long time ago, 2014, 2015. Why I choose this example? Because this is a good example about the noise. Okay, so let's go to question number 2 about the noise. So if you see previously, students answer directly in the answer book. So student directly answer in the same in the answer questions, and then they need to submit. Okay, this one. Okay, so you see that the question number 2, explain the term of intermodulation distortion. Okay, intermodulation distortion is due to the 2 or more signal, which this is in the notes. Disebabkan oleh due to the 2 or more signal that produce a cross product. Okay, you can answer from the from here, from this one. Okay, is the generation of unwanted sum and different frequency when 2 or more signal are amplified in a non-linear device. And you need to provide a figure, a simple figure, which is figure B, like this. Okay, that means you need to explain and provide the figure. Okay, simple. And then question number 2, question B for this one. So an analog receiver system consists of an antenna and 3 cascaded RF amplifiers as shown in figure 2B. The system operates at 17 degrees Celsius. That means 290 Kelvin. Okay, and you are given the bandwidth of 300 megahertz of bandwidth. So the system looks like this. You see that it has an input signal power 5 watt. There's no input noise. Input noise is not given. You have 3 amplifiers, RF1 until RF3. There's no output SO and NO is not given. Okay, you are given A1, A2 and A3. And then TE1, TE2 and also TE3. Okay, so you see the difference here. We give A3 is equal to 20. Okay, so this is not dB, this is 20. Similar with this one, TE1 is 77 Celsius. This is actually in Kelvin, 300 Kelvin. So I forgot to put the value here, K. This is Kelvin. Okay, determine the input signal to noise ratio in dB. How much is the input SNR in terms of decibel? Okay. So maybe we can open a wait. Maybe I can open a whiteboard so that I can show you. Wait. So I will open a whiteboard. Okay, and maybe we can try. Okay, so side by side like this. Okay. This is a good example. This is a good example to try. Okay, so you see that you are given the temperature, ambient temperature. Okay, you are given the ambient temperature is 17 degrees Celsius, which is equal to 290 Kelvin. So, okay, 290 Kelvin. Okay, 17 plus 273. Okay, maybe I will show you like this. So it is actually equal to 17 plus 273. So this is 290 Kelvin. Okay, 290 Kelvin. You are given the bandwidth. The bandwidth is given as 300 mega. Okay. So you don't need to write this because I already gave you this example, the answer here. So you just need to help me to calculate. Okay. So now the first question asks to find the input SNR. Okay. So we know how much is SI. SI is given. Okay. SI is given as 5 watt. Okay. So I don't know how to increase the size of this one. Okay, 5 watt. Okay, how much is the Ni? So Ni is actually equal to KTB. Okay, so this is equal to 1.38 times 10 power of minus 23. Okay, multiplied with 290 Kelvin multiplied with 300 megahertz. Okay, so you will get this equal to so ini boleh cuba kira. You can try this. Okay. So I get this one around 1.2 picowatt. Okay, 1.2 times 10 power of minus 12 watt. Or you can say that this is a 1.2. Okay, okay. Try to use your calculator. Help me to calculate. Okay, and the question asks in terms of dB. Okay. So okay, SNR in terms of dB. So that means you need to. So I go to the next page. So SI over NI. This is equal to 5 watt divided with 1.2 picowatt. Okay, picowatt. So you get this in terms of 4.167 times 10 power of 12. Okay. So in terms of decibel, this is equal to 10 log 4.167 times 10 power of 12. So this is equal to 126.198 dB. Okay, you can try. Cuba Okay. And then what? If I'm wrong, please correct me. If I'm wrong, please correct me. Kalau saya kira salah, tolong betulkan. And then what? The second question asks you to find the total noise factor. In order to find the total noise factor, you need to calculate F. You need to find a F value for each of the amplifier. Okay? So therefore, we can find F1 until F3. So F1 is equal to 1 plus TE1 divide with T. So this is equal to 1 plus TE1 is given as 77 Celsius. 77 Celsius in terms of Kelvin, you need to plus with 273. So you get 350. Okay, so you get 350 Kelvin divide with 290 Kelvin for the room temperature. Okay, so this one you get 2.201. So this is 2.201. Okay, and then find the F2. F2 is equal to 1 plus TE2 over T. So this is 1 plus this is Kelvin, 300 Kelvin. Okay, this is supposed to be Kelvin, divide with 290. So K ni tak perlu letak pun tak apa, no need to put the K. Okay, so this is equal to 2.034. 2.034. Okay, and then F3 is equal to 1 plus TE3. This is equal to 1 plus 450 Kelvin divide with 290 Kelvin. So you get 2.552. Okay, 2.552. Ini boleh cuba calculator. Okay, and then what? Find the total noise factor. So from here you can find the total noise factor F total. So I use the next slide. F total is equal to F1 plus F2 minus 1 divide with A1 plus F3 minus 1 divide with A1 multiplied with A2. Okay, so this is equal to 2.201 plus F2 minus 1, which is 2.034 minus 1 divide with 2.512. Remember, you need to do the anti-log of 4 dB. Okay, anti-log of 4 dB, you will get 2.512. Don't put 4 here. Okay, be careful. Plus F3 minus 1. F3 minus 1 is 2.552 minus 1 divide with A1 is 2.512. This is anti-log of 4 dB multiplied with anti-log of 5 dB. Anti-log of 5 dB you'll get 3.162. Okay, 3.162. Try use your calculator. Cuba guna calculator. This is equal to 2 point berapa ni? Boleh try 2.201. Okay. We're 2.512. 0.412 plus 0.412 plus so 0.195 0.195. So I get this one 2.808 okay. Okay. If you don't understand, please ask. Kalau tak tahu, tak faham, boleh tanya. So the third question, okay, the third question say that find the output signal power SO in watt and output noise power NO in dBW. So how to do that? Okay. So I use the next slide, the next slide, this one. So we need to find SO and also the NO. Okay. So therefore, in order to find the SO, SO is easy. SO is output signal power is equal to input signal power multiplied with all the gains. Okay. So you can find the gains. A total is actually equal to A1 multiplied with A2 multiplied with A3. Okay. So how to find this? This is actually equal to anti-log of 4 dB 0.4 multiplied with anti-log of 5 dB 0.5 multiplied with 20. So I get here around 158.866. Okay. And then what? From here I can find the SO. So SO is equal to A total multiplied with SI input. S input signal power. So what I get is that 158.866 multiplied with 5. Okay. Input here is 5 watt. So I get here is 794.328 watt. Okay. Okay, so what's next? Okay, what's next? Find NO. In order to find NO, you need to first of all you need to find the SNRO. Kamu kena cari SNR dulu, O dulu, barulah boleh dapat SO ataupun NO. Then you can find the output noise. Okay. So in order to find NO, first of all you need first, because we already know the F total. Okay. So we already know the F total from the previous. We already find F total is equal to 2.808. Okay. We already find the SNR input, already known, which is which is equal to 4.167. So 4.167 times 10 power of 12. which is equal to 126. 198 dB. Okay, so remember that F total, if you remember F total is equal to SNRI divide with SNRO. Okay, so SNRO is equal to SNRI divide with F total. Okay, so what you can do is like this. So SNRO is equal to SNRO is equal to this one 4.167 multiply 10 power of 12 divide with F total is 2.808. Okay, so you get this one around ni boleh cuba so 4.167 exponent 12 divide with 2.808, so I get 1.4839 sorry 1.484. Okay, this is SNRO. Okay, and in order to find so let's go to the next part. So SNRO, we already find this is equal to 1.484 times 10 power of 12, and we already know the SO. We already found the SO. So SO is given as 794.328. Okay, what? So in order to find SNRO, SO over NO, SNRO is equal to SO over NO. So therefore NO is equal to SO over SNRO. Okay, which is equal to 1.484 times 10 power of 12 divide with 794.328 watt. Okay, sorry, betul lah. So how much is this? Okay, oh sorry, terbalik sorry. Sorry, it's opposite direction, sorry. So this is supposed to be so this is supposed to be SO 794.328. Okay, divide with 1.8484 multiply 10 power of 12. Okay, so this is what? So you get how much? Okay, so 794.328 divide with 1.484 exponent 12. So we get 5.352635. Okay, 3526 times 10 power of minus 10. Betul lah Cuba try. Can you try? Are you do you get the same answer or not?
Same.
Okay. So this is in term of what? But the question asks in term of dB. Okay. The question asks in term of dB. So 10 log of this. So 10 log of this you will get. So 10 log 5.353526 exponent minus 10. Okay, so you get minus 92 minus 92.714 dBW. Okay, you get the same answer? Sama tak jawapan? Anybody?
No, Dr. Which?
Okay. Boleh this whiteboard has been shared to you through your email. So you don't need to write the answer actually, because you can refer this later. What you need to do is you can try to use your calculator to find the answer. Okay, help me to find the answer using your calculator. Okay, any question you can ask? Any question you can ask? So the last question, the receiver input signal to noise ratio can be improved by using a suitable configuration for the cascaded RF amplifier system. In your opinion, which RF amplifier should be placed at the first stage and why? So the question asks, we can actually improve the system by reconfiguring the arrangement of the amplifiers. So which amplifier should be placed at the first stage? Okay, because this is the first stage. You see that? Okay, this is the first stage amplifier, second and third. So according to this question, there are many ways to improve the SNR, of course. Okay, so one of the method is by rearranging the amplifiers. Okay, salah satu cara untuk improve SNR, to improve the SNR at the output is to rearrange the amplifiers so that we can have less noise factor and improve the output SNR. So how to do that? So we need to refer to the previous this one. Okay, so if you see from here, with this kind of arrangement, we get the total noise factor of 2.808. Okay, and in order to improve this, what we can do is that we need to put the first amplifier to have the least noise factor. Amplifier yang pertama perlulah amplifier yang mempunyai noise factor yang paling minimum. Okay, followed by the next least noise factor, and then the highest noise factor should be put at the last stage. Okay, so that means based on this, we can see that the lowest noise factor is this one. Okay, this is the lowest noise factor, followed by this one, number 2, and then the last one is this one. Okay, So therefore, when you want to suggest the arrangement, it should be like this. Amplifier 2 followed by amplifier 1 followed by amplifier 3. Okay. So why I choose this? I choose this because we need to put the first stage of amplifier to be the amplifier that has the least noise factor, followed by amplifier with second least noise factor, and then the last one will be the highest noise factor. Okay, based on the previous experience, students tend to use choose amplifiers with the highest gain, which is incorrect. Okay, which is wrong. Okay, which is wrong. So you need to choose amplifier with the least noise factor. Okay, so the reason you choose this combination because you put the least noise factor at the front side. Okay, and the question doesn't ask you to prove. If the question asks you to prove, then you need to find the new F total. I'm sure, okay, I'm confident, I'm sure that the new F total is less than this one. Okay, less than this one. I'm sure that the new total total noise factor is less than this one if we do the combination like this. Okay, you will get a new F total less than this one. Okay, but the question don't ask like that, so you just need to prove the combination. You just need to show the combination and the reason why. Okay, we choose this because the first stage of amplifier need to have the least noise factor, followed by the second least noise factor and the highest noise factor, so that we can produce the lowest noise factor, overall total noise factor. The idea is to have the minimum total noise factor. That's the idea. Okay, the idea is to have the minimum total noise factor. Okay, so that's all for today. So I managed to complete one chapter, chapter 2 for one day. Okay, so hopefully you are not feeling tired. Okay, so now you can take the attendance. Okay, you can take the attendance. You can open your QR code and you can scan, and then you can go out. Okay, after this you can go to the Bazaar Ramadan, okay, to buy food. Sorry for the late. I'm actually I plan to finish earlier, but because of the example, I take 20 minutes to answer the example question. Okay, so you can scan and then you can go out. Okay, so see you again next week, and please make sure that you already found your group members. Okay, I will give maybe the project instruction by this week, maybe. Okay, so that's all for today. Thank you.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Okay, welcome.
Thank you, Doctor.
Welcome.
Thank you, Doctor.
Okay, welcome.
Doctor, scan.
Tak boleh scan.
Khairul-Hafiz.
Nama siapa?
Muhammad Khairul-Hafiz.
Muhammad Khairul Hafiz. Dah ke? Khairul Hafiz Abdul Rahman.
Ya, saya.
Okey dah.
Doktor,
Siapa nama?
Gabriel pun nak dapat.
Gabriel. Okay,
Ya,
Gabriel.
betul,
Okay,
Dok.
dah.
Terima kasih, dokter.
Okay, sama. Who else?
Muhammad Abdul Karim. Muhammad Abdul Karim.
Muhammad Abdul Karim. Okay, Muhammad Abdul
Yes, dokter.
Karim. Okay, done.
Okay, thank you, dokter.
Okay, welcome. Who else? Tak dengar. Siapa? Tak dengar lah.
Amirul Amri.
Amirul Amri. Muhammad Amirul Amri. Adam.
Yeah.
Okay, done.
Thank you, Doctor.
Okay, welcome. Who else? Siapa lagi belum?
Doktor saya, doktor.
Siapa?
Syarif.
Saya Syahim.
Muhammad Syarif.
Muhammad Syahir.
Muhammad
Muhammad
Hamsyad.
Syahim, Syahim Azim.
Ya.
Okay, done.
Syarif.
Okay, doktor.
Hamsyari Hamizan.
Siapa?
Hamsyari Hamizan.
Syahria Mizan. Okay, done.
Thank you, doktor.
Okay, who else? Ada lagi? So, kalau tak ada, saya stop sharing I stop sharing.
Salam, doctor.
Yeah? What's your
Doctor,
name?
one more question.
Pardon?
One more question that I cannot understand. Can
Okay.
I ask you?
Okay, sure. What? Yeah, have you take your attendance?
Yeah, attendance I already take, but the example test question.
Okay, okay, okay. Which one?
Yeah, this one.
Sorry, wait.
First step, wait, 350, doctor.
Okay. So, your question is?
F1.
F1?
1 plus 350 to 90.
F1?
Yeah, F1, doctor. Where did you get 350?
Oh, 350 from 77. This is in terms of Kelvin. Okay.
Yeah, it is
so,
formula.
so 77 degrees Celsius plus 273.
Oh,
So you get 350.
77 plus what?
77 plus 273. Okay, so 77 plus 273. This is to convert from Celsius to Kelvin.
Okay, doctor. Thanks. I understand now.
Okay?
Thanks a lot, doctor.
Okay.
Okay, bye. Have
Okay,
a good night, doctor.
Okay.